Okay, hello, welcome to another video. In this case, we will do exercise number 1 of the handout of the Fourier Transform lesson. In this case, they are asking us to calculate the Fourier transform of a certain function. There is a typo here. Let me just correct it. The typo that is in the definition of the signal that we need to Fourier transform, and because the Fourier, sorry, okay, the Fourier transform is not that we need to calculate is not of the signal xt that is here, but really is x of t is equal to the exponential of the absolute value of t. Okay, this is the exercise that we are going to do, which is the one that makes more sense. Okay, so let's go ahead. So first of all, let's take a look at this signal. How does it look like? So if we plot this, basically it's the exponential in absolute value, which is something like this, what I am writing here. So this is value 1, and this is the way it is. It looks like. Okay. So in order to do that, what we just see is that this signal is just two signals added together. We can think that it is composed of a first signal which represents the positive part of the signal, so this one that we will call for example x1 of t, for example, and also added together this other signal which is just the negative part, this one here. Okay, this we will call it x2 of t, so that our signal x of t is just x1 of t plus x2 of t. Okay, and you will see why I do that, because I'm going to play around with the symmetries of the signal. So what they are asking us is to calculate the Fourier transform of this, that we can call it x capital X of the frequency omega, and this will be capital X1 of omega plus capital X2 of omega. Okay, so let's now play a bit with that. What we see is first that our signal xt always take real value, so it's a real value signal. And remember that for any real value signal, there is a property of the Fourier transform, which is if x is a real value, then its Fourier transform is anti-hermetic, which means that x omega is the same as x conjugated of minus omega. So this is anti-hermetic property. Hermetic property. We say that the signal that verifies this is an hermetic signal. So if x is real, then its Fourier transform is hermetic. So why do we that? Because look, x1 and x2, they are opposite signals. So basically what we can say is that this is, for example, x1 of t plus x1 of minus t. So x2 really is the reflection of x1, so x2 is x1 of minus t. So if this is the case, then what we can put is the following thing. Look at this, x1 of omega, we can say it's exactly the same as x conjugated of minus omega. So x1 of omega verifies this property, so this is the same as x1 conjugated of minus omega. Okay, and x2 of omega, what we have seen, this is the same as x1 of minus omega. Okay, why? Because this is the Fourier transform of this, so it just reflects the variable minus t in minus omega, and we just use the fact that x1 is real to say that the Fourier transform is hermetic. So look at this, we have a certain Fourier transform and the same which is not conjugated. So you know that if we add two complex which are one conjugated of the other, the result is 2 times the real part of the conjugated number. So in this case, this will be 2 times the real part of x1 of minus omega. Okay, so we are a bit closer. We have simplified and just play a bit around with the symmetries of the signal, and we come over here. But let's take it a step further. And remember from the table of Fourier transforms that we had a Fourier transform that resembles this one. We calculated, or we put in previous, or we calculated in previous exercises, that the Fourier transform of this is a divided by a plus j omega. And this is very, very similar to what we have. What we have is basically a is equal to 1, and a is equal to 1, because this is a2 minus t. So basically what we have is a minus t u of t. This is x1 of t. Okay, you agree? x1 of t is this, which is a minus t u of t. Okay, so with this formula what we get is that this is 1 divided by 1 plus j1. Okay, so look, we have the Fourier transform of x1 of t, which is x1 of omega, which is this. So we are almost there. Why? Because let's calculate the real part of this. Okay, what is the real part of x1 of omega? So the real part is very easy to calculate. You just multiply the numerator and the denominator by the conjugate of the denominator, and we will get basically 1 divided by 1 plus y squared. Okay, so this is the real part. I won't go ahead into the details. You know how to calculate it. This is what you get, and what you can see is that this is exactly if we, as w is a square, this is a symmetric function, so this is exactly the same as the real part of x1 of omega. You can see that this is exactly the same. Okay, so, and this is exactly what we want, the real part of x1 of minus omega, which is over here. Okay, so finally, if we go all the way over here, we will get that x omega, which is the Fourier transform that we have, is 2 times the real part of x1 of minus omega, which is 2 times 1 divided by 1 plus y squared. Okay, so this is the result that we were looking for. Okay, so I hope that it is clear. I think it's interesting exercises because we had to put in place the symmetries. First, the hermetic symmetry of the signal, which is the case because it is real, okay, this symmetry. And then we put into place the fact that the Fourier transform of x of minus t is x of minus omega. Okay, so in this case, remember, if I have a signal which xt, which has a Fourier transform x omega, okay, the Fourier transform of x of minus t is x of minus omega. This is another important property of the Fourier transform, which is what I put into place over here. And once I have that, I made use of this Fourier transform to calculate the real part, and this is what I plugged in here. Okay, thank you for your time. I hope you enjoyed the video, and we will see each other in another video. Bye-bye.